difficult to find something new and unknown in such old and well investigated
And сейчас мы подождем. Последние. Так, а может мы начнем? The first talk will be done by me, and because my co-chairman Valery Tucci now is at home, please take me the moment when will be maybe 3 or 5 minutes to the end, and I will be talking about BRSA analysis for medical applications using laser photoacoustic spectroscopy and machine learning. It's a very attractive approach for example, analysis of various metabolites associated with biochemical process in the body, and of course fast non-invasive screening tests. And it's a very promising approach, but we do not see this method of diagnostic in the market and the medical practice, and there are several problems connected with the long way to put it to the market. And the first general methodological problem that typical volatile molecular metabolites, which can be measured in BRSA, have low specificity. Here you see example connected with several pulmonary diseases, and you see that there are no unique molecules which will be specific for some definite disease. There is solution of this problem if you have ability to detect big number of similar molecular metabolites, maybe 15, 20, as you can see on the right table, the example connected with lung cancer diagnostics. You can achieve high enough accuracy. Also, very important to pay attention that there are two methods of bioatomics implementation. First, connected with so-called chemical-based approach, when at the first stage you extract information about content, about concentration of the breath samples. It's typical for gas chromatography. And after that, you can use this information for diagnostics. Another approach, it's so-called pattern recognition approach, when you measure some characteristic of the breath, not directly associated with concentration. It's typical, for example, for electronics noise devices. And similar patterns also allows you to detect some specific disease. Interesting that in this situation, classification rule looks like black box, and it's not typical for medicine, because medical specialists always try to understand what is, for example, chemical background. But in any case, this approach also is useful for fast screening tests. And in independence on the method of implementation, on the last stage, of course, machine learning is very useful to create data model for classification. First technical problem when we try to use laser absorption spectroscopy connected with necessary to have a very wide tuning range of laser source. You see here that, for example, once again, for pulmonary disease, you should have tuning from 3 microns to 11. And of course, no lasers can achieve these requirements. We solve this problem using optical parametric oscillator. You see here good enough spectral tuning range and ability to detect not less than 20 metabolites simultaneously. So it's quite good technique for us. But if you use OPO, we met another technical problem because we have very wide spectral width of OPO generation line. And we have solution of this problem associated with using computer super resolution reconstruction method implemented through deep learning networks applications. What is super resolution reconstruction? It's typical approach for improving quality of images, and this method allows you to create high quality image instead of low quality image. There are various variants of implementation of this technique, and in our case we use situation when trained artificial network have association between low resolution data and the same high resolution data. In our case, spectrum. You see here some details of our simulation, the example of high resolution spectra and low resolution spectra. In our case, resolution was 1 and 5 reverse centimeters. And the architecture of our network is combination of encoding and decoding parts, and right picture real architecture, and some details about method of modeling. We created spectra of poor components. After that, we synthesized mixture spectra, add noise, random noise, use filtration, etc., etc. Here is the example of implementation of our technique. Red line is low resolution noise spectrum, and two other lines are high resolution spectrum and predicted spectrum. You see that there is no difference. We do not see difference between two last examples. So this neural network works very well. Please, next slide. Back. Thank you. Here you see some statistics of simulation with various variants of spectra. To achieve quality of restoration of resolution, we use a special person-like correlation coefficient. The idea is to compare two spectral curves in numbers, And here you see results of calculation of this parameter for our spectra after restoration of resolution. And left picture without application of filter processing, and right picture with application of Gaussian filter. You see that results are quite good, especially for moderate level of noise, and of course preliminary pre-processing improve quality of resolution reconstruction. Also to analyze usefulness of this approach in analysis of experimental spectra, we make a simulation for solution of inverse spectral problem. We used gas mixture containing eight components with concentration presented here, and after that we try to provide decomposition of the spectrum. Here you see by blue color situation with initial high resolution spectrum. Red color corresponds to analysis of low resolution noise spectrum, and yellow data corresponded to analysis of reconstructed spectrum. You see that there is no difference between initial high resolution spectrum and restored. So this method is quite good to improve quality of complicated gas mixture decomposition. If you try to use chemical-based approach, we can meet with another methodical problem associated that we have too much components in gas mixture, like breath, air, and which is unknown. And in this situation, typical method for complicated gas mixture decomposition do not work, like multivariate curve decomposition. And we have two solutions of this problem. First, connected once again with using deep learning methods. Here you see some information about simulation and training of our deep learning network. The architecture is presented here. And some results of restoration of concentration. This network works quite good, but in rare situation with when some components have lower concentration, there are errors, and interesting that when concentration is decreased, the error is increased. And to take it into account, to remove unstable data, we create a special method, special criterion to validate data less than 5%. For example, the error can be more than, once again, 5-7%. So we can use our network, and after that we can check our data and remove unstable data. Another method of solution of this issue connected with very interesting method based on reducing of spectrum complexity when we remove exactly one of the components. Here you see left picture example, gas mixture by blue line and some specific component marked by a red line, and when we remove this red component, we achieve the minimum of this parameter. To validate this approach, we provided some simulation with very complicated gas mixtures with very big number of components with various concentrations. And here you see results of application of this method to restore concentration of only one component from this gas mixture And you see that relation between real concentration and restored concentration is perfect in the situation without noise, and also in situation when the noise was 10% relativity to mean value of amplitude of absorption spectrum. It's very high noise. So this method is quite robust. And we implement this technique for BRSA analysis, and I will show one example connected with acute myocardial infarction detection. Here you see the list, short list of some specific for this disease component, which can be measured in breath, and some details about groups on the study, patient with myocardial infarction and controls. First, it's so-called pattern recognition approach. Sorry. Так. Еще. Все, спасибо. Here you see machine learning pipeline which was implemented. Preliminary we provided optimization of every step of this pipeline, and the idea of optimization was connected with achievement of the most high specificity and sensitivity on the final stage. And here you see final results of optimization and validation of created predictable model. You see that specificity and sensitivity is 86%, it's high enough. And also we implemented a chemical-based approach on the same data. We applied a method which was mentioned above to extract concentration of typical biomarkers, molecular biomarkers in the breath for this disease. You see information about these results, and after that we created several predictive models with various variation of used biomarkers, and you see that when we use 6 biomarkers, the specificity is 93% and sensitivity is 82%. Also it's high enough. So in conclusion, I would like to say that deep learning networks is very good tool for bryoatomic application, especially in ice situation using wide tuning range laser photoacoustic spectroscopy. And interesting that our method, experimental method, photoacoustic absorption spectroscopy, allows us to implement the pattern recognition, a chemical-based approach using the same data. Thank you for your attention.
Thank you very much for a very interesting talk. My question is, you focused in your work on detecting gas molecules characteristic of certain diseases. The question is this approach and this method capable of detecting viruses in the breath air, like in COVID case?
It's not a simple question because viruses do not have metabolism, but if you will use some experimental technique to measure some characteristics, spectral characteristics of viruses, why not? Our method of analysis can be applied for any data in any field, for example, for liquids, for tissues, but you only should use another experimental technique. Okay.
Another question, if I may. about in the 90s, so about 20 years ago, the technique of diode laser spectroscopy was developed by Novoderyozhkin, Stepanov, and they also use it for solving this problem. So can you compare the efficiency of these approaches?
Yes, thank you. Very good question. There are various techniques for example, from the field of laser absorption spectroscopy. Diode lasers is quite good for detection several specific components. But to provide diagnostic of any disease, as you can see, you have to have ability to control big number of metabolites, 20. Diode lasers do not allow you to measure such a very big number of metabolites, but they are quite good to control some specific metabolites. So it's a rather different technique. Okay, I think it's enough for my talk, and we should go forward. And the next talk will be done by Zeev Zalevsky. I see Zeev here.
Yes, I'm here. Yes, I hear you. I'm here.
Do you hear us?
Yes, I can hear you. Yeah.
Yeah, excellent. Please upload your presentation.
Yeah, I checked. I could make a screen share, so it's fine. Can you see my screen?
Yes, yes. Please switch to full screen mode.
Yeah, sure.
Excellent. So, it's invited talk, and you have 20 minutes.
Starting from now?
Yes. Yes.
Okay. Okay. So, thank you very much for allowing me to present my work. And by the way, do you see my camera or not? 1 second.
Zeev, please once again switch to full screen mode.
Just 1 second. Okay.
We see you.
Yes, good.
You are look good.
Very much. Okay, now I'm ready.
Yeah, excellent, excellent.
Okay.
Once again, you have 20 minutes from this moment.
Okay, so thank you very much for allowing me to present my work. I'm from the Faculty of Engineering at Ireland University in Israel. And today I'm going to speak with you how lasers can be involved in the world of biomedical sensing and diagnostics. The outline of my talk will be divided according to the following structure. I will give an introduction about a new remote photonic sensing technology that could be used for the biomedical diagnostics. I'm going to show you some research backgrounds and show you how this technology is applied in clinical biomedical diagnostics. And finally, I'm going to conclude my talk. So as I guess, as some of you may know, this film of Star Trek, which is a science fiction movie that was displayed in the cinema and in the television, say 50 years ago, the doctor of the spaceship used a special device which is called tricorder. And with this device, he could sense from a distance large variety of biomedical parameters of the subjects that were facing this specific sensor. So my news to you is that this is no longer a science fiction. Actually, this is the technology that we have developed during more than 10 years of research in my faculty, and about 6 years ago it was commercialized to a startup company. It evolved into a product, and about a year ago it received an medical FDA approval. The technology is based upon the following operation principles. So the sensor that we use has a laser, camera with special optics, and special image processing algorithm. We illuminate the subject that is facing the sensor with the laser, and the backscattered light from the tissue of the subject is forming this self-interference pattern, which is called secondary speckle pattern. Due to special optics that we have in our sensor, we can analyze the full pattern, not to compute the contrast of the speckles, as many people do, but rather to analyze the full two-dimensional pattern and check how the spatial statistics of the speckle is changing in time, and from this to deduce vibrations occurring in the tissue that was illuminated by the laser with nanometric precision. So actually what we do sensing of nanometric vibration, of nano vibrations occurring in the inspected tissue. Since nano vibrations in general, when they have nanometric, and when we have a nanometric precision of sensing it, they are actually the common denominator to almost any biological and biomedical process occurring in our body. And therefore, by sensing those vibrations, we can use them in order to extract simultaneously and continuously very large variety of biomedical parameters. And by having those parameters, we could we can have a much wider medical image about the medical situation of the subject and use it to perform medical diagnostics. Everything is from a distance, continuously and in real time. And what you saw here is actually a saying of Albert Einstein that also agreed with what I'm doing by saying that everything in life is related to vibrations, so I fully agree with this. So we worked on this technology for more than 16 years, 10 years in the university, and about 6 years after that in a startup company that I co-founded. And in this company, in the university and later on in the company, we developed various prototypes. You can see here different prototypes. The larger the prototype of the sensor is, the larger is the range from which the sensing could be performed. And if we talk about sensing done from only a few meters away, the sensor could be really, really small sensor like you see in this picture, in this slide where I mark with my mouse. Now, the various types of biomedical parameters that we were sensing with the sensor could be divided into several categories. Actually, more or less 3 categories. The first category is sensing of vital biosigns. The second category is molecular sensing, sensing of various chemicals in the bloodstream in a non-invasive way. And the third category is hemodynamic sensing, sensing of the flow characteristics of our blood through the various blood arteries. And by sensing various biomedical parameters along those 3 categories, we extract the full biomedical or medical picture about the subject and do our medical diagnostics. Those prototypes evolved into products. You can see here various versions of the product. Some of them are low-end versions, some of them are high-end versions, some of them are add-on, which are integrated with a smartphone, as you can see on the right side of the slide, and some of them are standalone. You can see here a measurement example of a subject facing our sensor. The sensor is analyzing scattered light, and therefore we don't even need to see the subject. We can perform the sensing through smoke. And yet extract, as you see in the right side of the slide, extract various biomedical parameters. In this case, it is the heartbeats, the phonocardiogram, not only the number of beats, but also the shape of the beat, the beating, the respiration, number of respirations, the sound of the lungs, and so on. This is an example of vital biosigns that we could measure with our sensor. Now, in the next 3-4 minutes, I will briefly go through the 10 years of research in which we use this sensor to prove that we can sense large variety of biomedical parameters, such that in the next part of my talk, I will be able to use this knowledge or background in order to show you how usage of all this large number of biomedical parameters could indeed be used for medical diagnostic purposes. So in this case, I will start by sensing vital bioscience. In this case, in this slide, I show you how we sense heart beatings, how we sense breathing. By the way, in all the measurements I'm going to show you, there are always two colors, two charts. One is measuring with our sensor, the other one is measuring with the medical benchmark in order to show, to validate that indeed our measurement is accurate and correct. Obviously it is, this is why we got FDA, but still what I'm showing you now was done in the research stage in which we developed the technology. So here we measure the respiration, here we measure the heartbeats, the charts you see here, this is the phonocardiogram, the sound of the heart beating of two different subjects. We measure blood pressure. You can see here a chart, green and blue. The green one is our measurement, the blue is our measurement, the green is the measurement with the medical benchmark, which is the cuff you put on your hand. All those are vital bioscience. But as I said, the first category was measuring of vital bioscience, the second category was molecular sensing. So we showed also the capability of sensing of various chemicals in our bloodstream. In this case, in this slide, I show you how we sense concentration, non-invasively of course, concentration of lactate in the bloodstream. In this case, the measurement was performed following the following mechanism. The higher the concentration is, it causes micro vibrations to our muscles. The lactate acid appears in the blood when we use the muscles, for instance, if we jog. You can see, for instance, in the measurement in the left side, you see different colors. Each color corresponds to different concentration of lactate that we measured by taking a blood sample. And we measure those nano vibrations occurring in the muscle with our sensor. You see that by changing the concentration in the blood, we have stronger nano vibrations, as well as the frequency, the specific frequency of the nano vibration is also changing. We also measured another chemical in the blood, for instance, concentration of alcohol. In this case, we did it by measuring the change in the phonocardiogram of the beating of our heart. We examined a single period of the beating, and we showed that when you drink more and more alcohol, within the single period, between one beat and the next, the amount of noise that the heart is making between the beats is getting smaller as function of increasing in the alcohol concentration. So all this is very clear because it is related to nano vibrations that we are measuring. We also measured oximetry and coagulation and try to sense the hydration of the different subjects that participated in our clinical trials. Another very important molecular sensing that we performed included non-invasive sensing of glucose in the bloodstream. In this case, what we did, we combined our sensor that senses nano vibrations with external stimulation of magnetic fields. We used a very unique property that glucose has and other chemicals in the bloodstream do not have, which is Faraday rotation or magneto-optic effect. So we applied external magnetic stimulation. Due to this stimulation, because of glucose, there was a phase difference between the circular right and circular left polarizations of the photons interacting with the blood. And due to this, the self-interference pattern, which is the secondary speckle pattern, was changing in time. And this is what we analyzed with our sensor. So we could relate the measurement of the speckles that we do with the photonic sensor with the change in the concentration of glucose in the bloodstream. And in preliminary clinical trials that we have performed, we were able to show that in around 96% of the results that we have measured, we had less than 15% error in comparison to the glucometer, which is our gold standard. Glucometer extracts blood from the blood veins and measures directly the concentration of glucose there. We did it in vivo measurements. We did it also in a very controlled in vitro measurements. So we put a cuvette with glucose in different concentrations and applied them, so put it in a solenoid, applied magnetic fields and measured the way I told you. You can clearly see the change in the value that we measure for the vibration or change in the speckles versus the concentration of glucose. You can see here more measurements. The third category that I have mentioned is the category of measuring hemodynamic activity. And the main application we are working in our lab is related to measuring hemodynamic activity of the brain. And today, the best way of doing it is using functional near-infrared spectroscopy or EEG recording. In both cases, they require a helmet that looks similar to what I show you in this slide. On the other hand, when we apply our technique, this is our sensor and one of the subjects participating in our experiment, we do the measurement from a distance continuously without using a helmet. What happens is that when we do a stimulation of a specific cortex in the brain, in this case it was stimulation of the visual cortex, so the cortex needs oxygen. The oxygen arrives to that cortex due to the blood flow. Blood flow is pulsating. Pulsation is vibration. So we can sense vibrations and therefore we can sense the brain activity of that specific cortex. In this case, we put two sensors, two cameras. Every camera is another sensor. And you can see, for instance, measurements here in the lower part of the slide done on 3 different subjects. You can see, for instance, in A, no stimulation of visual cortex. We see at the beginning no vibration, and then there was a stimulation of the visual cortex, and you see that the measurement is increasing in its value, which means that through our speckle-based sensing, we sense vibrations because blood arrives to the visual cortex due to the applied external stimulation of the visual cortex. And this happens in all the 3 subjects and in all the subjects that participated in our experiment. So far, I spoke with you how to do sensing of biomedical parameters. The next step was to develop various biomedical devices that could make medical diagnostics. The diagnostics are related to vibration because this is what we measure, but as I said, this is the common denominator to almost any medical condition and biomedical parameter. Here we do experiment in which we combined our sensor with a medical device, with a stroboscope, and we try to measure anomality in the vocal cords. But in our case, we can do it externally or internally, as medical doctors do. We could choose, in any case, the vibrations of the vocal cords is what we measure, and we could sense difference between the 2 vocal cords, and through this, detect anomalies which could be related to various pathologies, medical pathologies. You can see here the experiments of measuring the vocal cords from inside the throat. You can see the vibration frequencies, and you can see the diagnostics we do. Another type of medical device we have developed is related to otolaryngology. In this case, we were detecting otitis, which is inflammation in the ear. So we put our sensor on top of this ENT, throat, nose, and ear device, and measure the vibrations of the eardrum while we are doing its external stimulation. So we had a loudspeaker that vibrated the eardrum at certain frequency, and we measured the responsivity to this vibration with our optical sensor, and we saw that people which were healthy, those are different subjects. You can see, for instance, here, the responsivity, the elastography of the eardrum for healthy people was different than the one of people that had otitis, this inflammation, because the elasticity of the eardrum was different due to this inflammation. We also applied the same concept to extract bones fractures, because we measure elasticity, and if there is a fraction, the elasticity is different. We measure intraocular pressure in the eye, which is related to medical eye medicine, to a disease called glaucoma. When the pressure, intraocular pressure is increased, the elasticity of the eye is changing. We applied it for early breast cancer detection. The elasticity of the breast is changing. This is instead of mammography. We did it for melanoma detection, again, by changing elastography of the skin, and skins with pigmented lesions or melanoma, its elasticity is different, and the responsivity to the infrasonic stimulation done with our loudspeaker, the responsivity that was measured with our optical sensor gave different results that could allow us to diagnose melanoma or pigment or lesions of the skin. Okay, the last part of my presentation is how to use the sensor. So I spoke with you how to sense many biomedical parameters. I spoke with you how to incorporate this optical laser-based sensor into medical devices. And the last part now, the one that I'm going to talk about in the next 2 minutes, is a large-scale clinical trial that we have performed in which our sensor, our product, did full medical diagnostics in large-scale clinical trials conducted in one of the medical centers in Israel to early detect various types of cardiopulmonary diseases. So, and this is the first ever remote sensor for this type of diseases. Here we had an experiment in which we had 115 patients, and we were using this sensor to perform a remote diagnostics of arrhythmia. We were able to show in those clinical trials precision and accuracy of more than 99% in detecting this arrhythmia. Another disease that we tried to detect was atrial fibrillation. Again, we did those clinical trials in one of the medical centers in Israel. We used 444 patients, and we were able to show with our sensor sensitivity of not more than 92% and specificity of detection of more than 96%, which is quite high. The last clinical trial we performed was applying our sensor to perform diagnostics of cardiopulmonary disease which is called congestive heart failure or pulmonary congestion. In the clinical trials, we had 227 patients, and we were able to show sensitivity and specificity of performance, which were more than 91%. This is the only ever sensor that can do this. So in order to meet the strict time limit, I will conclude my talk. I spoke with you about this remote photonic sensor that analyzes the temporal spatial changes of the backscattered speckle pattern, and using this analysis in order to sense nanovibrations and apply the nanovibrations to simultaneously sense many biomedical parameters which are either vital biosigns or molecular chemicals in the bloodstream that we sense or hemodynamic activity. Then I showed you how we can use our developed prototype to demonstrate its usage for biomedical detection and sensing applied in medical devices in which we try to detect bones fractures, melanoma, breast cancer, intraocular pressure, changes of intraocular pressure, otitis, which is the inflammation in the eardrum, vocal cords anomalies, and more. And in the last part of my talk, I showed you how this sensor can participate in large-scale clinical trials in which we try to detect cardiopulmonary diseases, which were, while the diseases that we demonstrated in our trials involved arrhythmia, AFib, and congestive heart failure. Thank you very much for your attention. And if you have questions, I will be glad to answer them. And I hope I was more or less in time. Thank you.
Thank you, Zeev. Very interesting talk.
Hi, Zeev. I'm
Hello.
Sasha Priyezov. Great talk, very informative.
you,
Certainly lots of questions, but we have limited time, so I will answer the only one most important for me. You surely know that during the last probably 2 decades, millions of dollars were invested to design a contactless technique to measure glucose in blood. Yeah? And now you seem to be close to solving this problem. As far as I know, so dozens of physical techniques were tested, and most, next to all of them showed sensitivity of changes in glucose level.
But not specificity.
Yeah, and mostly in vitro. But when you start implementing these techniques in vivo, nothing happens. So it turns that you have to make calibration each time you measure. So the problem of calibration. So do you face this problem? How often do you have to calibrate your device? Thank you.
Thank you very much. This is an excellent question, Sasha. I was very quick in my explanation because I had only 20 minutes, but you touched a very important point. So first of all, many technologies try to detect glucose in a non-invasive way. Most of them were using spectroscopy-related sensing, which gave a good detection capability, but very low specificity. So they were mixing their measurement with other chemicals because concentration of glucose is very low. It's about 0.1%. We started doing the measurement with a unique property of a magneto-optic effect that glucose exhibits, and there are very small number of chemicals in the bloodstream that have this property, and therefore we were able to get not only high precision means up to 15% from the glucometer, but also very high specificity. Actually, my first measurement was done in vivo, and I was able to show relatively good results on a group of people, say up to 20 people, after doing calibration, of course, but still good results. And because people didn't use this effect before for glucose measurement, actually people told me, okay, in vivo, you don't really know what you measure because there are so many parameters. Show us in vitro that indeed what you measure, the phenomena that you use for your high sensitivity and high specificity measurement is indeed correct. So our next step was to do the in vitro. We started with in vivo and then we did in vitro, and we showed that indeed we can have high specificity and high sensitivity. Now, related to your question of calibration, you are definitely right. We need to calibrate. But we do the calibration, not a general calibration, but a person-wise calibration. We show that our calibration holds for a few weeks, let's say two weeks, approximately 2-3 weeks. It depends, of course, on how you do the calibration, how much data you collect, and how sophisticated is your machine learning algorithm that you use. But a few weeks, it could hold. So our intention, by the way, or our application, is not to have a device that completely doesn't use pinching the finger and extracting the blood, but rather doing it once 2 or 3 weeks instead of doing it several times per day. Moreover, I'm not aiming for a medical grade in this case, for this application. I'm aiming for the wellness application, in which the required precision is lower because it's only an awareness or a medical tool for doing recommendation and not for making a medical diagnostics. And when I work within this environment, I do believe that this unique effect, together with the advances that we have in the algorithms of AI and machine learning, we will be able to do it sufficiently well with this every 2-3 weeks calibration process.
Okay, thank you.
Thank you.
Have you any questions?
Yes, I'm sorry, I was listening.
Yeah. Hi, Zeev, it's Vladimir Zaitsev. Excellent talk as usual.
Hi.
So my question relates to your statement about the possibility to measure internal ocular pressure. different techniques usually apply some additional stimulus and measure some reaction of the eye. And to please elucidate what was the stimulus and how you decomposed the pressure from the mechanical properties of cornea.
Yeah, definitely. So we do a stimulus. I said it in my presentation. I apologize if it was not clear enough. I do infrasonic stimulation. I have a loudspeaker that makes a stimulation in different frequencies, 100, approximately 100, 200, 300 hertz. And the optical sensor is measuring, our optical sensor is measuring the responsivity to the stimulation. So practically it measures elastography. Now, how can I separate between the IOP and the mechanical properties of the cornea? So the point is that I'm doing the measurement, first of all, in several different stimulation frequencies, infrasonic frequencies. Second, I'm doing it by not making a sinusoidal stimulation, but rather stimulating in pulses. So I have also a parameter that allows me to measure the rise time and the fall time per stimulation frequency. And I also do the measurement not in one optical wavelength, the responsivity. I measure it in 2 or 3 optical wavelengths, and every wavelength has different properties of penetrating into the tissue, and therefore the different information has some orthogonal components that after training my AI and machine learning algorithm, it allows me to have good measurements with high precision. And actually for this type of application, we are not far from getting medical precision. And in this application, we are quite progressing in evolving it. We are now in a process of making larger scale, still not very large, but medium scale clinical trials. It looks promising. There is still a lot of work to be done, but for this application, I believe it will be able to get a medical grade that will give a precision of around 1 millimeter of mercury, which is the precision of Goldman tonometer.
Okay, thank you, and thank you once again to Zeev. Very interesting talk. Good luck for you. And
thank you very much.
We should go forward, and the next talk will be done by Grigory Gelikonov. Non-invasive, non-obvious features of low coherence interferometry from Institute of Applied Physics. Please.
First of all, I would like to thanks for organizers for inviting me, and I will talk about some not obvious things in low coherence interferometry which may be interesting for people. Most famous application of low coherence interferometry is optical coherence tomography. And optical coherence tomography is a very good model for presenting these non-obvious things in low coherence interferometry. So, optical coherence tomography utilizes light in so-called transparency window near-infrared region of optical radiation, and when we use light with relatively broad spectrum, it provides quite short interferometric response in interferometer, and this determines resolution in depth. So, quite good technique and very useful for medical diagnostics and very widely applied in medicine. And what we would like to do with this, we would like to see deeper, and for this we have to increase signal to noise ratio. And for this we have to do two things, increase optical power and decrease noises. And for example, let me have pure electronics without any receiving noise. Let's see what we have in this case. So this is generalized input electrical circuit with photoreceiver as detector and electrical load, which converts photocurrent into voltages, and here we have signal and noise. Signal is proportional to intensity, and noise has three components which is fundamental and could not be eliminated. First is thermal noise of electrical load, shot noise of photons, and relative intensity noise, which provided by beating of independent spectral components of the light. And relative intensity noise proportional to inverse proportional to square root of bandwidths, optical bandwidths of our light, and relative intensity noise proportional to intensity itself, shot noise proportional to square root of intensity. And here we have dependence of these three noises of intensity, light intensity on our receiver. So thermal noise doesn't depend, it's obvious, it's just thermal noise of resistance. Shot noise goes like square root of the intensity, and relative intensity noise goes proportional to the intensity. So here we have several points when different noises are equal to each other, and it is obvious that if we raise intensity, we will the noises will be determined only by relative intensity noise, and rising intensity of the light, we will not increase signal to noise ratio. It will be constant after some values of input light. So, could we do something with this? Here is. Let we have microphone type interferometer with broadband light source here. Here we have device under testing. This picture came from low coherence interferometry, but not from optical coherence tomography. So here we have an object in optical coherence tomography and device under testing here, and reference part has some attenuator. So signal to noise ratio determined by two intensities, thermal noise, shot noise, and relative intensity noise. It expressed in ratio of powers of signal and powers of noises, sum of powers of noises. So usually we have power of light came returned back from our object much less than the reference power. In this case, we may do quite tricky thing. We may reduce reference power by attenuating it, and it was shown that there is an optimum which goes quite close to fundamental limit, and it allows us to attenuating light in the reference arm almost achieve highest possible signal-to-noise ratio. And it was shown experimentally as well. And this is first not obvious thing is in low coherence interferometry, because it's quite counterintuitive that you have to attenuate light to have higher signal-to-noise ratio. And one may mention that let me do this coupling not equal, but it will not work with interferometer, Michelson type interferometer. It's quite easy to show that splitting ratio 50-50 is optimal for this type of interferometer. So this is not the end. If we have equal interferometer with equal intensities came from both arms. For example, we need these for compensating path difference in the probe in the optical coherence tomography. So here we have compensating interferometer, which we need to re-establish interference. And this interferometer has equal intensities in both arms. So we have same noises, and the only question, what bandwidth, what optical bandwidth we have to apply to calculate exact value of optical noises. So why we ask this question? We use light source with spectrum like this, let's say. And when we have interferometer with equal intensities in both arms, we have interference like this. So as we can see, not all optical components present in this spectrum. So this means that this noise will comprised by not all optical components. So in other arm we have additional spectrum to this, and if we calculate it carefully, we may see that without interference we have some value of this noise, which is inverse proportion to optical bandwidth. And if we take into account this modulation factor, we'll have noise square root 1.5 times higher. So it was also demonstrated experimentally with spectrum modulate like this. On the graph on the right side we can see short noise, which was obtained by thermal light source, and two lines without interference and with interference. It's quite obviously we may see that our predicted dashed lines lies quite good in the experimental ones, experimental points. So this is it was not obvious thing, and we didn't see these features, or let's say exact noise value calculation in previous works. So one more thing with low coherence interferometry. For good in-depth resolution, we use wide spectrum of the light, and in this case we face the problem of dispersion compensation, which could spoil our resolution depth. For example, let we have a light source with spectrum of this blue line, and let we use just a narrow band of this with this green line, and left column will present signal with dispersion, and right column will present signal virtually without dispersion. So, if we apply a higher and higher bandwidth, wider bandwidth of light, without dispersion, we'll have higher and higher resolution, and left column show that resolution stop grows, and then resolution became even worse. So this well-known feature of influence of dispersion mismatch in interferometer arms, and from very beginning, special components of physical compensation of dispersion were applied into interferometers, and it was quite sophisticated. So some part of water and two different glasses, two different type of optical glasses were applied to compensate this influence of dispersion. And as well, it was numerical approaches to compensate this dispersion. And I would like to mention that it was applied very tricky thing. Maybe good. Maybe not all of you know about fraction Fourier transform, which means that you make Fourier transform with not hard to explain. Okay, fraction Fourier transform has some additional phase coefficient in it, and it virtually rotate this plane of image and initial signal and Fourier image graph in certain angle, and it compensates some kind of dispersion when we can observe in our experiments. So, but still we have, even we can compensate it numerically, we have to find it first. So I will show you on the example of time domain optical coherence tomography, time domain interferometry, when we record interference signal physically moving one arm, change one length of one arm of interferometer. So we have spectrum, and with interference dispersion we have signal like this gray number 1 instead of these two sharp spikes without dispersion. And the signal we can express like sum of signals from each scatterer, because we record optical field and electrical field, let's say, and it just has no influence to one to another scatterer. So signal spectrum of this signal contains spectrum itself and phase factor. And if we have media with a quite low quite low dispersion in media itself, we may put this phase factor of dispersion mismatch interferometer out of brackets of this summation, and then we may calculate correcting functions and apply to the spectrum of our signal and restore pure not distorted signal of our interference. So it was recorded like this and recalculated like this. And then, good, I'll do it faster. Okay, let me have a very distorted image, and let me try to find dispersion curve with polynomial-like function with ninth order. It still may have not good compensation of dispersion. You can see this point is definitely not compensated. So what to do in this case? Let me have dispersion like red curve, spectrum like blue one, and let me calculate our signal using just small part of our spectrum, this green line. We may see that a dispersion curve in this region is quite linear and has a definite slope, and this slope provides shift of our signal up and down. We may calculate signal with each position of this narrow band. It may be called as Gabor transform, and after that we have picture like this on the left lower part of the slide, and we may see a position of our signal for each point of our narrow band filter, and this represents slope of each position. Summarizing, integrating these will have doesn't work after that. We'll have actual dispersion function, and using it we'll have, in comparison of these 2 points, pure image without any influence of the dispersion. And one more minute, I would like to show this. When we record image of living object, anytime we have this motion artifact, because we have we need time to scan it, and each time we scan we have fast axis and slow axis. Picture represents cross section of slow axis and phase cross section of in certain depths here, and many people use correlation technique to find how far object moved between scans and try to compensate it, but this technique may provide distortion of image, because if the object is not flat, it could be flattened after these calculations. So, but we have interference signal, and image itself has a clue how to compensate this mode, and I will explain it very shortly. When we have 2 A scans, sequential A scans, they have regions on the outside, which are not correlated because it was acquired from different part of our tissue, and region of the cross section is the same. It's principally the same part of the tissue, but recorded in different times. So we may calculate phase difference between these two A scans. It will contain only phase difference in this cross section. We may summarize it over all scan and compensate it. You'll see we did not make any decision during calculation. We just calculated. It was blind calculation, and it should play. Okay, here. This real-time compensation. You may see how it moves on the left side and quite stable on the right side. So I have a couple more slides, but I think this is enough for just a final presentation.
Okay, thank you, speaker. Really good results. Short question.
Thank you very much. Very interesting approach. The question is, have you already implemented this approach to a working system, and what is the outcome?
Yes, all things we did for real application in real life. So yes, we did it, and for eye imaging we still have no working machine itself. We have just experimental machines. So, but for dispersion, some other things, yes, we did it.
Okay, so thank you, speaker, once again. Very fantastic results for analysis. And we should go forward, and the next talk will be done by Elena Kiselyova. The title of talk you see here. 15 minutes.
Okay, dear colleagues, good day to all. I'm glad to participate at this conference, and today, in general, my talk will be about the transferose application of optical coherence tomography and optical coherence tomography angiography in open and laparoscopic surgery. As you can notice, the title of my talk is difference from the declared in the program. It is because I combined two presentations in one, my and my colleague Maxim Rybkov, who is a surgeon, and I'll present our results in one presentation. Okay, let's start. And the main questions that I plan to talk about are the following. First, we will analyze the spectrum of pathological conditions in abdominal surgery where rapid objective tissue evaluation is required. Then we see the different methods for interpretive assessment of tissues during surgery and determine the place of OCT and OCTA among other methods. Then we talk about why it is very important to stabilize the tissues during the acquisition the OCT data, and especially angiography images. And then I'll talk about OCT and OCTA for ischemic injury of the small intestine in open and laparoscopic surgery. And finally, I'll say about how we can apply OCT and OCTA for monitoring of the enterostomy condition. So, urgent abdominal surgery is in dire need of an instrument for objective diagnostics of blood circulation and structure of the abdominal organs, especially in cases of acute mesenteric ischemia, when diagnostics of tissue viability should be done for optimal resection, and subsequent detection of blood supply in anastomosis and in stoma is also required. It should be said that in case of stoma, surgeons have only empirically estimated time period when the intestine is ready for reconstruction, but they need more objective methods to assess the tissues for the decision. And another clinical task is detecting the presence of stones and small stones in the biliary tract, because the preoperative ultrasound investigation didn't show all the stones that can be in biliary tract. And if in laparoscopic surgery the surgeon didn't know about addition concrements, it can be an application in complications of for the patient. Okay, and if we look at the different interpretive bioimaging methods that can be used in abdominal surgery, we can see that each of them has their own technical characteristics, resolution, scan depth, study procedure time. Most of them show only data on blood circulation or perfusion, and this is not enough to determine the viability of tissues, especially areas of necrotic tissue isn't detected during these methods, and only OCT can simultaneously give information about blood circulation and the structure of the tissue. And as we can see, the main characteristics of this method is enough to become OCT, the promising method for surgical application. So, on the first stage of our research, we apply OCT and OCTA for investigation of acute intestinal ischemia. The study was performed on the small intestine of 27 rats, 22 in acute mesenteric ischemic group and 5 in control group. And then we also we perform pilot clinical study, and 27 patients were enrolled. There are also 2 groups, control without ischemic injury of intestine and patients with acute mesenteric ischemia. In the group of acute mesenteric ischemia, 3 regions of interest were scanned. It's area with maximum damage and with necrosis, border of ischemic area with norm, and normal intestine. And we used multimodal optical coherence tomography device that operates in the 1 0.3 micrometers wavelength, and with a special resolution 10 micrometers axial and 15 micrometers lateral resolution. Two types of probes were used: elongated OCT probe for patients and short one for animal study. And after OCT scanning, all the samples were existed for evaluation with histology. And we evaluate the signs of necrosis, ischemia, and inflammation. So here is the results that we obtain in experiment. Rat intestine is visualized with OCT and OCT-A to the full depth. OCT-A provides real-time imaging of functional blood vessels and determine their localization within the intestinal wall. We can see that normal state, ischemia with reversible damage, and ischemia with non-reversible damage, in particular with necrosis of different layers, can be quite good differentiated between themselves by angiography images and by cross-sectional OCT structural images. We can see the different density of vessels in each state, and the structure of cross-sectional images changes. But these findings couldn't be translated to patients very easy, because we scanned the intestinal wall of the patients and revealed that the microstructure of intestinal layers in patients is more informative than in small animals, because each of the layer of patients is increased, so we can easily detect the peritoneum edema and intramuscular fluid buildup, which is indicated with arrows, and also necrosis makes the OCT images structureless and homogeneous. Therefore, real-time differentiation between necrosis and inflammation with edema can be easily done. But the main problem we face is the main problem with angiographic images, because the pronounced peristaltics of human intestine, different respiratory movements and other motions of the body increases the rate of images with strong and multiple artifacts. And you can see that angiographic images of human intestine are not so qualify with, in comparison with animal one. So for CT, it's very important to stabilize the organism during the acquisition of angiographic images. And in human, it occurs that only 10% of angiographic images have minor artifacts and 74% have multiple artifacts, whereas 15% not informative at all. So the aim of our study were to develop a method for atraumatic local fixation of intestinal wall to increase the percentage of high-quality artifact-free images which can be obtained from patients in surgical operating room. And for this purpose, we designed a special vacuum cap that put on the top of the OCT probe, And this cap is connected with the suction pump to, to create a negative pressure in the space of the cap, and tissues can be stabilized, locally stabilized. So the geographic images became very clear and artifact-free. And it's very important not to damage, not to disturb the microcirculation during the use of this vacuum cap. And it was estimated that the pressure in the vacuum cap should be about 60 millimeters of mercury. So I have time, two presentations. Yes. I have a combined report, yes. Okay, and the second stage of our study was to approbate our vacuum cap in different objects and mini pigs in patients in stoma of patients and in rabbits laparoscopically. And here you can see the stages of usage of the vacuum probe. When aiming is performed, then scanning process, and then you can see that no damage in the place of vacuum cap placing you can see. We scanned 25 different areas of small intestine of normal pigs. Firstly, without use the vacuum cap, and then the same places were scanned with the designed cap, and we show that the number of OCT and OCTA images containing motion artifacts was reduced from 84 in manual fixation to 8% using the vacuum cap. And we also histologically confirm that there is no damage in the places where we use the vacuum fixation. So it's safety procedure to increase the rate of the artifact-free and geographic images. And this is an example how vacuum cap can be applied for monitoring of one place of intestinal wall during ischemia. You can see that during the time the blood vessels disappear and reappear, and to the 13 minute we observe the increase in blood vessels number, and we can assume that in this time compensatory mechanisms included to save the tissues during ischemia. And again, we can't see any signs of damage on the surface of studied tissues that improves the safety of our vacuum cap. So this is an example how blood vessels visualization and structure of the stomach can be performed in patients. So if we manually fix the probe on the surface of the tissues, you can see that numerous bright lines appear in angiographic images, and we can't see any blood vessels, but when we use the vacuum cap, the stabilization of tissues is achieved, and the angiographic images become more clear. And the same thing is observed with the structural images, especially in face. And it's interesting that in the stoma there are different places where we can observe multiple blood vessels and their absence, which were not studied and not known by surgeons before this investigation, and we propose that this new data will be helpful for objective evaluation of the tissues and help to make a decision when the stoma ready for reconstructive surgery. Okay, and this is an example of monitoring blood vessels and tissue structure of the ileostomy from 6 to 30 days. And we can see also that the serous membrane is changed during the period of time, and also the structure of villi also changes, and we can monitor the microcirculation of the mucosal membrane and the serous membrane, and this information can be helpful too for surgeons. And the last point of my talk is the laparoscopic application of the OCT. Here I can say that in this case, in the laparoscopic surgery, we used long probe. This is the first requirement to perform this kind of investigation. And we also used the vacuum cap, of course, because inside the body the movements are very high and pronounced, and without tissue stabilization there is no available data. And in case of laparoscopic surgery, the good application of OCT can be the detection of stones in the bile ducts and gallbladder. And here you can see that in case of empty gallbladder, the wall of this organ can be seen, and the empty space. But if we have concrements in the ducts and in the organ, it can be easily determined by OCT, and it can help surgeons during the removal of quite big stones that is detected by ultrasound. But OCT can help during the intraoperative surgery to detect also small undetectable before stones, and this is quite a requirement in the surgery. Okay, to conclude, I want to draw that a method of local tissue fixation using a vacuum cap is proposed. This allows significantly reducing the number of motion artifacts in OCT and OCT images of large laboratory animals in patients. OCT-A allows diagnosing ischemic damage to the small intestine wall in open and laparoscopic surgery. Vacuum traumatic tissue fixation enables multimodal OCT monitoring of the enterostomic condition and possibilities of OCT in the detection of stones in the gallbladder and bile ducts was demonstrated laparoscopically. Thank you for your attention. This is our research team. I want to thank also the Russian Science Foundation for the opportunity to perform this study. And if you have any questions, you can ask me. Thank you.
Okay, thank you. Thank you. It was 2 reports. Do your colleagues have any questions? My question may be a comment. Some of your results can be well analyzed by machine learning for diagnostic. What do you think about combining your OCT with machine learning analysis of images?
Thank you for the questions, and I think it's very yes, I agree, because there are numerous images that we obtain from tissues, and quantification methods and the machine learning are quite required for the OCT, because numerous data collected, and it will help to analyze images more objectively, because one can see the layer and another person cannot see this layer, and this is quite subjective, and machine learning will help in this. Okay, thank you.
Okay, thank you, speaker, once again, and we should go forward, and the next talk will be done by Dmitry Tarasov from Belarus.
Добрый день, коллеги. Меня слышно? Можно как-то?
Да, слышно.
Рационализировать.
Вы будете по-русски говорить? Do you hear me, Dmitry? Я понял, я не туда смотрю. Okay, we see a presentation.
Коллеги, добрый день еще раз.
Пожалуйста, переключите в полноэкранный режим. Мы видим презентацию, но она пока...
Сейчас.
F5 нажмите. Вы по-русски будете говорить?
Да. Можно на русском языке выступление?
Вы далеко, мы вам не можем запретить. Так,
хорошо.
Все, спасибо. 15 минут.
Так, еще раз здравствуйте. Представляю вашему вниманию доклад на тему сравнения противоопухолевой активности фотосенсибилизатора на основе инвертрикационного красителя и фотолона. Скажите, слайд переключается? Просто иногда бывают проблемы. Да. Переключается, да? Значит, фотодинамическая терапия сегодня занимает одну из ведущих позиций среди современных методов лечения злокачественных образований. Это стало возможно благодаря высокой локальности фотодинамического воздействия, которое является сочетанием двух факторов, а именно возможности локальной фотоактивации фотосенсибилизатора и его высокой избирательности накоплений. В основе этого метода разрушение опухолевого очага активными свободно-радикальными частицами, которые возникают в результате взаимодействия фотоактивного соединения, или еще называют фотосенсибилизатора, с лазерным излучением определенной длины волны. В принципе, это не новая информация. Дальнейшее развитие методов ФДТ связывают с созданием фотосинтезаторов нового поколения, сегодня говорят о фотосинтезаторах 3-го, 4-го поколения, требования к которым не ограничиваются только высоким терапевтическим эффектом. Сейчас у нас имеется некоторое представление об идеальном фотосинтезаторе. Основные требования к ним представлены на слайде. Ключевое направление здесь – это разработка новых фотосинтезаторов, которые активируются светом в окне, так называемом окне прозрачности биологической ткани. Это область где-то 700-900 нанометров. Это позволяет повысить глубину повреждения, так, с одной стороны, так и глубину диагностики. Глубина повреждения большинства современных разрешенных к применению в клинической практике фотосинтезаторов на основе порфиринов – это 8-14 мм. В нашей лаборатории целенаправленно ведется разработка фотосинтезаторов на основе трикоциониновых красителей, которые характеризуются высоким малярным коэффициентом в окне прозрачности биотканей. Максимум поглощения располагается на 740-750 нанометров. Квантовый выход флуоресценции сопоставим со значением с эффективным флуоресцентным зондом и в значительной степени удовлетворяют требованиям, которые определяются к идеальному фотосенсибилизатору, то есть обозначенному выше. Помимо этого, относительная простота модификации структуры делает их достаточно уникальной платформой для различных приложений. То есть мы можем путем модификации структуры придать нужные необходимые фотофизические свойства, ну, медико-биологические свойства в том числе. Соответственно, по результатам комплексных исследований последние десятилетия фотофизические свойства ряда интеркарбоциониновых красителей в модельных средах и опухолевых моделях на экспериментальных животных in-vivo нами выделен краситель с оптимальными свойствами для тераностики злокачественных образований. Структурная форма его приведена на слайде. Приоритетным направлением модификации структуры красителя у нас было обеспечение новым соединением высокую растворимость в воде и биосовместимость, низкую темновую токсичность и высокую избирательность накопления в опухолевых тканях, сохранение выраженного фотодинамического эффекта под воздействием излучения в окне прозрачности биоткани. Отличительными особенностями его структуры является наличие ортофененового мостика в цепи сопряжения полиметиновой цепи сопряжения и двух цепочек полиэтиленгликоля с молекулярной массой 300 дальтон, которые ковалентно связаны с концевыми группами. На данном этапе разработки нами оптимизирована схема синтеза красителя с частотой конечного продукта более 99%. Разработан прототип лекарственной формы, исследована фармакокинетики накопления и получены достаточно высокие результаты по фотодинамической эффективности на нескольких опухолевых моделях экспериментальных животных. Проведены, помимо этого, токсикологические исследования. В данной работе мы бы хотели продемонстрировать эффективность нового фотосинтезатора путем сравнения его терапевтических свойств с разрешенным к применению в клинической практике препаратом. Для этого решено использовать отечественный фотосинтезатор второго поколения «Фотолон», который выпускается предприятием «Белмедпрепараты» и является комплексом производных хлорина Е6 с поливинилпирилидоном. В настоящее время он широко используется в клинической практике, его применение оказалось эффективным для лечения неоплазии шейки матки. Излечено около 2000 больных, при этом регрессия составляет порядка 94%. Фотолон, тем не менее, имеет максимум поглощения длине волны 666 нанометров, и глубина повреждения тканей при ФДТ с ним составляет 8-14 нанометров, в том числе и в некоторых в экспериментах, проведенных нами, а не только на основе данных его разработчиков. Значит, для сравнения фотосенсибилизаторов исследована их противоопухолевая активность на перевивной опухолевой модели лабораторных животных. Для получения объективной картины при сравнении фотосенсибилизаторов исходили из того, что необходимо обеспечить оптимальные условия использования для каждого из испытуемых аппаратов. Протоколы использования фотосинтезаторов на основе интеркарбоционинового красителя и фотолона различаются, тогда как параметры проведения ФДТ должны быть идентичными как минимум по следующим пунктам, а именно одинаковая опухолевая модель, способы введения препарата и параметры светового пятна на поверхности опухолевого узла. Исследования противоопухолевой активности таким образом мы проводили на половозрелых и вредных мышах, самках линии C57BL6 в соответствии с протоколом по проведению доклинических исследований фотосенсибилизаторов. На наружную поверхность бедра мышей перевели ацетитную карциному Эрлиха. При этом для перевивки опухоли мышам подкожно вводился разведенный с серийным 0,9% раствора натрий хлорида карцинома Эрлиха. Эксперимент для двух фотосинтезаторов проводили через 10 дней после перевивки животным в одном эксперименте. Опытные контрольные группы формировались из животных с опухолями, объем которых достиг 30-40 мм кубических, или, что соответствует линейным размерам опухолевого узла, порядка 4-6 мм. Доза в фотосенсибилизаторах, время начала фотовоздействия, энергия и плотность мощности облучения выбирались в соответствии с ранее проведенными исследованиями по оптимизации условий проведения ФДТ с каждым из исследованных фотосенсибилизаторов, при которых достигается максимальный противоопухолевый эффект для каждого. Соответственно, для нового фотосенсибилизатора исходили из собственных результатов исследований. Так, интеркарбоциониновый фотосенсибилизатор используется в виде прототипа лекарственной формы, смесь хроматографически чистого красителя с безводной глюкозой в соотношении 1 к 30. Начало фотовоздействия осуществлялось в соответствии с его фармакокинетикой через час после введения. Для облучения использовался полупроводниковый лазерный источник света собственной разработки. Для фотолона ориентировались на протоколы его использования. Разработчики фотосенсибилизатора фотолон выполняли исследования его противоопухолевой активности с использованием перевивных опухолей на лабораторных животных крысах. Так, для крыс доза фотолона при внутривенном введении составляет 2,5 мг на килограмм. Оптимальные условия проведения сеансов ФДТ с фотолона в экспериментах с переменными ухылями на лабораторных мышах могут быть выбраны, если учесть влияние особенностей метаболизма у мышей и крыс. Известна общая тенденция уменьшения скорости метаболизма с ростом размера тела животных. Это приводит к различию эффективных доз препаратов для разных видов животных. Алгоритм межвидового переноса доз описан в руководстве по проведению доклинических исследований лекарственных средств, откуда можно почерпнуть информацию, что коэффициент пересчета дозы в эквивалентную дозу для человека у мышей в 2 раза меньше по сравнению с крысами. Следовательно, доза препарата при проведении исследований с лабораторными животными мышами должна быть в 2 раза выше. Облучение проводили с помощью лазерного терапевтического аппарата ФДТ-лазер, разработки Института физики Национальной академии наук Беларуси, который разрешен в применении медицинской практики и предназначен как раз-таки для ФДТ с использованием фотолона. Исследования проводились для 2 групп животных с энергетической световой дозой 50 джоуль на сантиметр квадратный и 100 джоуль на сантиметр квадратный, чтобы соответствуют дозы в соответствии с его протоколом и в 2 раза больше. Плотность мощности составляла 150 милливатт на сантиметр квадратный. При определении начала облучения ориентировались на данные по фармакинетике для быстро растущей опухоли саркома М1 крыс, представленной на слайде. Максимум накопления достигается для крыс через 2-3 часа после введения, при этом на временном интервале 1-3 часа наблюдается плата по накоплению фотолона в опухолевом узле. Принимая во внимание более высокую скорость метаболизма у мышей, мы, соответственно, решили проводить облучение с фотолоном через 1 час после введения. Параметры ФДТ для обоих фотосинтезаторов приведены в таблице. Животные во время эксперимента находились под общим терапенталовым наркозом и дополнительно обездвиживались на специальной площадке с помощью фиксатора. С целью обеспечения одинаковых условий получения подвод возмущающего излучения выполнялось с помощью одного и того же световода с линзовым растровым рассеивателем. Это позволило идентичные параметры светового пятна на поверхности опухолевого узла. Для снижения уровня повреждения прилегающих к опухолевому узлу окружающих нормальных тканей применялся алюминиевый экран с отверстием над опухолевым узлом диаметр 10 мм, что обеспечивало достаточную засветку опухолевого узла. Опухолеактивность фотоинизаторов оценивалась согласно рекомендациям фармакомитета по доклиническим исследованиям лекарственных средств. В течение 21 суток проводилось наблюдение за состоянием животных и динамикой роста опухоли в опытных и контрольных группах. Измерения линейных размеров опухолевых узлов проводили в день проведения ФДТ и на 1, 3, 5, 7, 14 и 21 сутки после терапии. Состояние опухолевых узлов и прилегающих тканей дополнительно фиксировалось на фотографии. Для объективной оценки противоопухолевой активности рассчитывался коэффициент торможения роста опухоли, критерий излеченности и увеличение продолжительности жизни. Формула, как это рассчитывалось, приведена на слайде. Соответственно, какую картину мы наблюдали? На 3-5 сутки после проведения ФДТ у животных в испытуемых группах на месте локализации опухоли наблюдались ожоги с формированием струпа. Наблюдалось нарушение функционирования лапы. В целом, на 3-й сутки у животных опытных групп среди пораженных ожогом тканей не наблюдались опухолевые узлы, в то время как у контрольных групп они наблюдались и их размеры увеличились. Заживление ран у животных протекало достаточно быстро, однако неравномерно для разных опытных групп. Наиболее медленно этот процесс протекал у животных, которым вводился фотолон и проводилось облучение при энергетической экспозиции 100 джоуль на сантиметр квадратный. Нормализация состояния лапы происходила через 7-14 суток после облучения. На 14 и 21 сутки после проведения ФДТ опухоли не выявились ни в одной из испытуемых групп. В целом наблюдается одинаковая динамика роста опухоли после ФДТ для обоих исследованных фотосинтезаторов. Таким образом, при обеспечении оптимальных условий фотогенической терапии фотолон и новый фотосинтезатор демонстрируют одинаковую противоопухолевую активность для опухолевого штамма асцитной карциномы Эрлиха. На слайде приведены динамика роста опухоли и коэффициент торможения роста опухоли для опытных и контрольных групп. Фотолон относится к фотосинтезаторам второго поколения, в то время как идентификационный краситель по многим параметрам соответствует 3-му и 4-му поколению фотосенсибилизаторов. Так, идентификационный краситель характеризуется интенсивным поглощением и флуоресценцией в области 700-800 нанометров, где максимальное пропускание биологических тканей. Использование источников возбуждения с длиной волны в этом диапазоне повышает глубину повреждения опухолевых тканей. По нашим данным, на опухолевых штаммах для крыс мы получали некрозы до 20-30 мм. И глубину регистрации флуоресценции, помимо этого, мы можем достигнуть до 1,5 сантиметра, что расширяет его терапевтический и диагностический потенциал. Индекс контрастности накопления идотрикальцинина красителя в зависимости от опухолевого штамма, по нашим данным, лежит в диапазоне от 4 до 7, в то время как для фотолона этот параметр составляет 2–2,5. В экспериментах с лабораторными животными для идотрикальцинина красителя нами выявлена высокая скорость выведения. Через сутки после сеанса ПДТ его концентрация в тканях снижается на порядок. Для него установлена достаточно низкая токсичность и низкий уровень светобоязни. Таким образом, новый фотосинтезатор обладает противоопухолевой фотодинамической активности не хуже, чем для применяемого в клинической практике фотолона, а по некоторым важным для фотосинтезатора параметрам превосходит его. Спасибо за внимание. Может быть, есть какие-то вопросы?
Спасибо. Спасибо большое. Коллеги, есть вопросы? Не видно. Спасибо большое. Очень интересный доклад. Thank you. We should go forward. And the last talk, once again from Belarus. Виталий, do you hear us?
Да.
Пожалуйста, вы будете по-русски опять сегодня?
По-русски, да.
Загрузить, пожалуйста, презентацию. Ну, пока, значит, загружаете, Виталий Плавский, бактериальный бактериостатический эффект, global blue light, basic patterns and method for efficiency enhancement. Название появилось. Все, спасибо, 15 минут.
Хорошо. Уважаемые коллеги, мой доклад посвящен бактерицидному и бактериостатическому действию синего света. Значит, актуальность... Что не запишется? Значит, актуальность проблемы обусловлена прежде всего выявленной в последние годы устойчивостью, резистентностью микроорганизмов, патогенных микроорганизмов к действию лекарственных препаратов и прежде всего к антибиотикам. Эта проблема стала настолько важной, что Министерство, Всемирная организация здравоохранения проблему резистентности включила в десятку основных угроз глобальному здоровью, которые вот в настоящее время рассматриваются. Значит, считается, что через 20 лет может не найтись антибиотиков, способных оказывать бактерицидное действие на большинство патогенов. Поэтому интерес к действию света имеет очевидную природу. Считается, что антимикробная фотодинамическая терапия может быть одной из альтернатив при лечении локализованных форм инфекций. Значит, здесь мы рассматриваем тот метод, который не требует применения фотосенсибилизаторов для фотодеструкции патогенных микроорганизмов. Мы будем рассматривать те методы, которые основаны на фотодеструкции патогенов за счет красителей эндогенных, присутствующих в их составе. Но естественно, что такой метод имеет очевидное достоинство, так как не требует применения сенсибилизаторов, разрешенных к применению Минздравом. Значит, надо сказать, что клетки имеют грамм-отрицательный и грамм-положительный, имеют практически одинаковую чувствительность действия синего света, в то время, когда при использовании экзогенных фотосенсибилизаторов наблюдается разная чувствительность. Надо сказать, что бактерицидное действие было с ультрафиолетового излучения было установлено давно, и долгое время считалось, что таким эффектом обладает только коротковолновый ультрафиолет, спектр поглощения которого соответствует, спектр излучения которого соответствует спектру поглощения ДНК. Значит, однако в 1976 году появились работы, свидетельствующие о том, что и видимый свет способен инактивировать микробы, но с гораздо хуже эффективностью, чем эффективность ультрафиолетового излучения. Однако, несмотря на то, что эта работа появилась в хорошем журнале, долгое время она не привлекала к себе внимания, фактически потому, что отсутствовали источники, которые способны были оказывать такое выраженное действие, источники синей и фиолетовой областей спектра. Интерес к данной проблеме появился после создания лазерных и светодиодных источников, прежде всего длиной волны 405 нанометров, которая широко начала использоваться для подавления микробов. Значит, мы использовали в своих исследованиях целый ряд микробов, как из клинически выделенных, так и из американской коллекции штаммов микроорганизмов. Значит, и выполненные нами исследования показали, что воздействие излучения синей области спектра приводит к выраженной фотодеструкции микробных клеток различного типа, и это отличительная особенность, что излучение длиной волны 405 нанометров оказывает более выраженное действие, чем излучение 445 нанометров. Значит, и еще одна характерная особенность, что по мере увеличения энергетической дозы скорость фотоинактивации резко увеличивается. Значит, при переходе от длины волны 405-445 нанометров доза, необходимая для фотоинактивации 90% популяции микробных клеток, увеличивается в 3,7-6 раз. Значит, в то время, как показали наши исследования другого спектральные, что спектр поглощения порфиринов, которые могут быть ответственны за такое действие, падает при переходе длины волны 405 к 445 в 15, 20, 30 раз. То есть, значит, эти данные говорят о том, что какие-то другие молекулы, кроме порфиринов, участвуют в данном процессе. Значит, мы показали, что такими молекулами являются еще флавиновые молекулы, имеющие максимум поглощения в области 445 нанометров. Значит, мы разработали специальные методы экстрагирования порфиринов и флавинов и показали, что в клетках, микробных клетках присутствуют порфириновые, это копропорфирин, уропорфирин, значит, протопорфирин молекулы и молекулы флавинов. Мы оценили концентрацию, и оказалось, что концентрация флавинов находится в микромолярной области, а порфиринов в области наномолярных концентраций. Из-за такой существенной разницы оказалось регистрировать флуоресценцию порфиринов очень сложно, потому что, значит, кроме того, кроме различий концентраций, квантовый выход флуоресценции флавинов составляет около 20% в водных растворах, а порфириновых молекул, которых я называл, меньше 1%. Все это очень затрудняло регистрацию люминесценции порфиринов в микробных клетках. Значит, выполненные нами исследования показали, что вот здесь приведен спектр протопорфирина в соляной кислоте, и точно такие же порфирины регистрируются в одной из микробных клеток, в одном типе микробных клеток клепсиела окситока. Значит, внесение в суспензию клеток эндогенного порфирина позволило оценить концентрацию. Она находится на уровне 5 на 10 в минус 9 моля, то есть 5 наномолей, хотя в здоровых клетках концентрация порфиринов, по крайней мере, на порядок ниже в здоровых соматических клетках. То есть это говорит о том, что при воздействии излучения на ткань порфирины будут повреждаться преимущественно по сравнению с повреждением соматических клеток. Мы выяснили механизм повреждающего действия. Оказалось, что, ну, прежде всего, повреждение микробных клеток осуществляется с участием синлетного кислорода, что мы доказали, используя метод хемолюминесценции и добавление тушителя синлетного кислорода азида натрия перед облучением к суспензии приводит к тушению сигнала хемолюминесценции. Значит, дальше мы выяснили, что одной из причин гибели микробных клеток является повреждение мембраны микробных клеток, что контролируется по выходу ДНК в физраствор, в котором находились клетки при облучении. Повреждение ДНК, повреждение мембраны, извините, регистрируется и с помощью конфокальной флуоресцентной микроскопии, используя пропидиодид в качестве флуоресцентного зонда. Кроме того, наблюдается повреждение белков, что также значит, регистрируется по флуоресценции белковой компоненты, присутствующей в физрастворе после облучения. Значит, еще одной целью нашей работы была разработка методов усиления антимикробного действия. И мы показали, что переход от непрерывного лазера с длиной волны 405 нанометров к импульсному лазеру той же средней плотностью мощности 50 милливатт на сантиметр квадратный в случае использования наносекундного лазера повреждающее действие излучения с длиной волны 405 нанометров значительно выше, чем при использовании непрерывного лазера той же средней интенсивности. Понятно, что при использовании импульсного лазера амплитудное значение плотности мощности значительно выше, чем средняя плотность мощности для непрерывного излучения. Значит, тут дозовая зависимость, о которой я говорил в начале, и которая носит явный, значит, не экспоненциальный характер, увеличение скорости инактивации по мере увеличения энергетической дозы, мы обычно пытаемся объяснить тем, что в клетках накапливаются при воздействии света, образуются другие виды порфиринов, которые обладают более высоким сенсибилизирующими свойствами, чем исходные протоурокопропорфирины. Мы показали, что да, порфирин при воздействии излучения на микробные клетки разрушается. Это видно из спектра возбуждения флуоресценции, спектра флуоресценции. Но поскольку протопорфирины имеют высокие квантовые выходы генерации синлетного кислорода на уровне 80% в мономерной форме, то мы полагаем, что вряд ли образуются другие типы порфиринов, которые при значительном подсаживании спектра поглощения способны компенсировать более высоким квантовым выходом разрушение протопорфирина. И мы считаем, что причиной такого, значит, не моноэкспоненциальной вида кривой, а ускорения скорости повреждения микробных клеток по мере увеличения энергетической дозы является наличие многих мишеней, которые приводят к повреждению. И по мере того, когда на малых стадиях энергетической дозы микробные клетки успевают репарировать повреждения, которые вызывают излучение. По мере увеличения энергетической дозы клетки начинают не справляться с залечиванием повреждений, вызываемых светом, и наблюдается такой лавинная гибель микробных клеток, что приводит к резкому ускорению скорости их фотодеструкции. Значит, ну, по крайней мере, на это может указывать, на такой вид, на такое объяснение зависимости может указывать синергизм действия излучения, когда мы одновременно светим двумя лазерными источниками 405 и 445 нанометров. В этом случае повреждающее действие значительно превышает действие каждого из этих источников. Более того, такой же вид наблюдается и при воздействии излучения красной области спектра, когда одновременное действие двух источников приводит к более выраженному эффекту, чем по отдельности каждым источником. То есть такой синергизм, по нашему мнению, обусловлен тем, что лазерное излучение в этом случае адресовано различным клеточным мишеням, и способность клеток к репарациям повреждений значительно сужается по сравнению с действием излучения одной длины волны. Значит, таким образом, по нашему мнению, подход, основанный на использовании антимикробного действия синего света, он имеет такую клиническую направленность, и мы значит, в совместных исследованиях с медицинскими специалистами продемонстрировали эффективность применения света с длиной волны 405 нанометров для эффективного лечения хронических воспалительных заболеваний уха, горла, носа с лор-специалистами. Спасибо за внимание.
Спасибо. Так, пожалуйста.
Спасибо большое. Ну, у меня, может быть, несколько коротких вопросов есть. Во-первых, относительно длин волн. Вот здесь важна ширина спектра или нет? Вы проверяли, так сказать, свет от лазера и от пропущенный через синий стеклянный фильтр от лампы?
Нет, мы проверяли 405 нанометров светодиодный источник, ну, полуширина примерно 20 нанометров, да, и полупроводниковый лазер, ширина около 2 нанометров. Значит, эффекты равнозначные. А
если шире спектр, если взять лампочку и пропустить через широкополосный стеклянный фильтр?
Эффект будет зависеть от тем, что мы с лампочкой не сравнивали. Но понятно, что когда мы будем сравнивать поглощенную мощность порфиринами широкополосного источника и узкополосного, естественно, что поглощение будет отличаться. И мы здесь можем попасть как в сторону меньшего, так и большего поглощения в зависимости от спектральной ширины источника.
Понятно. Еще один вопрос. Вы сравнивали, значит, вот вы исследовали инактивирующие свойства синего света. Да. А допустим, нет бактерий этих. Если вы светите просто на здоровые клетки, вы инициируете как-то биосинтетические процессы? Ведь во многих работах было показано, что какая-то идет биостимуляция, да?
Да, я вчера делал доклад, в том числе по действию излучения на соматические клетки, то есть клетки, из которых мы состоим. Вот как раз по действию излучения 405 и 445 нанометров, да, мы, значит, ингибируем эти клетки тоже, значит, но причем они не гибнут в основном, а мы тормозим процесс клеточного деления на определенной стадии. То есть это такое регуляторное действие. Да, там есть составляющая, которая приводит и к гибели клеток. Мы это оцениваем с помощью метода проточной цитофлорометрии. Значит, но главную роль в снижении метаболической активности соматических клеток там вносит все-таки торможение клеточного цикла, замедление клеточного цикла.
Понятно, спасибо. Ну и последний вопрос, чисто клинический. Но раз такое хорошее инактивационное действие синего света, куда клинически светить надо? Ну вот вы говорили, что значит, да, ухо, горло, нос. Ну,
Да.
понятно, наверное, на слизистую горло,
Да.
носа. А если какие-то другие заболевания в легких там и так далее, что это, облучение крови или как надо оказывать воздействие световое?
Знаете, значит, один из методов – это внутривенное лазерное облучение крови, и излучение с длиной волны 405 нанометров используется в том числе для облучения крови. Более того, есть обширные данные, свидетельствующие о том, что использование излучения 405 нанометров для воздействия на кровь, которая находится в пакетах после переливания, для последующего переливания крови, такое воздействие не вызывает гемолиз эритроцитов крови, но способно инактивировать в том числе и вирусы, которые могут присутствовать в клетках крови.
Спасибо. Спасибо большое за очень интересный доклад.
Спасибо.
Спасибо. Dear colleagues, our session is closed and it's time for lunch.
When do we reconvene? When do we reconvene? Okay, as a co-chair of the whole biophotonic session, may I say a few concluding words? Well, yeah. Well, first I thank all of you who stayed here up to the end of our section, and we have already discussed. Actually, the level of the papers was rather high, and the level of English of those who spoke English was very high, and the papers were very informative, lots of new facts, interesting ideas. Internet section also worked well, and I would like to thank the technical group who provided the internet connection. Yes, and I thank all of you for your attendance of the conference. We have already had the program committee meeting. Usually when the conference ends, we announce where the next year conference will be held. You know that this is a yearly, annual conference. Well, unfortunately, at this time, at these conditions, it's difficult to predict what happens and where the next conference will be held. It will be organized. Well, as a probable place, Nizhny Novgorod is discussed, or Samara is discussed, and even Sochi is discussed. So we will explore the possibilities to organize a good conference in these places, one of these places next year. So thank you very much. So the conference continues, other sections will work after lunch, and you know that at 6:30 we leave on buses to the riverside, and we will have the conference dinner on board of a ship. The ship is reserved from 7 to 10 p.m. So approximately at 10 o'clock the dinner will finish. Well, thank you very much again, and good luck.
Hello. Let us start our last session and this section of laser matter interaction. By the end of this week, we have some changes. So the talk of Novodvorsky is cancelled. So we will have pleasure to see just now the presentation of Professor Lotin from Institute of Laser Information Technology from Shatura, which is devoted to laser-induced transistor dynamics in some thin films. Please, we give you the floor. You are not very much limited actually in time because we have two presentations cancelled, so feel free to pace in your way.
I see.
Okay.
Thank you. Dear colleagues, Mr. Chairman, I'm greatly honored today to take part in this conference, Advanced Laser Technologies. And first I would like to thank the organizers for invitation and the possibility today present the results of my scientific group. And the title of my presentation is Laser-Induced Phase Transition Dynamics of Germanium Telluride and GST thin films. Today is assumed that the end of the silicon transistors era is about 2030. And therefore, the photonics is considered as an alternative to semiconductor electronics, in which the slow electron storage information, while the fast photon can process, transmit, and storage information. And the advantages of photonic devices are obvious. They are high performance, high information transmission rate, noise immunity, low energy level of control signals. And for this reason, the efforts of scientific community and semiconductor industry last decade was aimed on finding new materials and development of new principles of process and storage information. And the greatest results in this direction was achieved in the field to development the neuromorphic system based on resistance elements, memristors, but however the photonic neuromorphic systems and optoelectronic devices great interest too. And one of the promising materials for this aim are phase change materials, such as tellurides, some tellurides doped by metals, selenides, and some antimonies. And special features of these materials are high contrast of physical properties between crystalline and amorphous phases, high reproducibility of phase transitions, high stability of phase states, and short time of phase transitions. It should be noted that the process of crystallization and reamorphization is significant different. And for example, in order to crystallize initial amorphous PCM, it is necessary to impact by pulse, for example, laser pulse with energy enough to achieve the crystallization temperature. While for reamorphize the initial crystalline PCM, the pulse energy is needed much more higher to achieve the melting temperature with subsequent fast cooling. before to create any devices based on PCM, it is necessary to study the dynamics of characteristics such as optical constant and conductivity induced by laser pulses. And samples under study, we have choose such famous flagship PCM as germanium telluride GT GST225 and new material gallium telluride. And the films with thickness about 100 nanometers of these materials have been grown on a substrate with different thermal conductivity. The substrates were used CO2, PC, sapphire, and zinc selenide. The experimental setup for investigation of dynamics characteristics is very simple and represents the pump probe method, where the pump we use two kind lasers, solid state nanosecond laser and titan sapphire femtosecond laser. And for probe laser, we choose the CV laser diode 1.5 micrometers. It was shown that by XRD method that initial state of our film is amorphous, and it is easy to crystallize this film by nanosecond laser to low resistance, low temperature alpha phase hexagonal phase and high temperature cubic beta phase with density energy and consequent reamorphization. And the surface of amorphous film is uniform, while for crystalline film the surface is granular. And it was determined that the GST film grown on substrate with low temperature, low thermal conductivity. The process of crystallization is occur in layer, and it is the crystallites are strong orient, and this process of crystallization is named as heterogeneous. While for GST film grown on substrate with high thermal conductivity, such as sapphire, the process of nucleation and growth crystallites are stochastically in full volume of film, and this process of crystallization is named as homogeneous. The study of transmittance and reflectance of our films, GST films, demonstrate that this material have huge, significant contrast of optical constants in near infrared region. And for example, for GST at wavelength 1.5, this is C band, the contrast is about 67% between the crystalline and amorphous phases. The studying of conductivity dynamics of GT films showed that the time of change conductivity for during the full crystallization is about 20 nanosecond, and for ramification, this time is about 50 nanosecond. And this process, crystallization and ramification, are possible as for one step, one pulse, and for multi-step, multi-level change of conductivity. The using of femtosecond radiation allows us to approach to the fundamental limitation of phase transitions, and we achieve about 2 nanosecond front of voltage change for GST film, and we assume that this process is associated with a sharp increase of concentration, photo-induced concentration carrier, charge carriers. And the long curve and our plot we associate with namely nucleation and crystallite growth. And exciting the phase transitions in by nanosecond laser phase transitions in GT film, we achieve the time of reflection change in film during full crystallization about 20 nanoseconds, and for transmittance about 30 nanoseconds. While for the ramification, this time constant were more 30 nanoseconds. Sorry. And for GST film, the behavior is similar, and of course, nanosecond lasers radiation doesn't us to allow the determine of limitation of phase transition rate. But this instrument allows us to realize reversible, reproducible, multi-level optical switching in both in GT film and GST film too. The studying of crystallization process in GST films induced by femtosecond laser allow us to determine, to measure the front of change of optical constant is about in nanosecond range, and these values were determined about 300 to 500 picosecond. This slide represents the process of ramification induced by femtosecond laser, and the reversible nanosecond jump, step we observed, and we associate this step with melting of film, short melting, and subsequent slow cooling of film. Of course, the presence of crystalline phases in our film we confirm by two methods, Raman spectroscopy and XRD method. And the femtosecond laser allows us to realize multi-level optical switching in GST film, and this multi-level switching of optical contrast nonlinear depends on the energy density and the number of laser pulses. As about new PCM materials, gallium telluride, the multi-level switching, optical switching, is realized too in these materials, and we hope this material is perspective for using to create the optoelectronic devices based on this material too. In conclusions, the time of optical constants, change of GST thin film induced by femtosecond radiation lies in sub-second region. And nano and femtosecond radiation provide multi-level optical and electrical switching in GST thin films, which has a non-linear dependence on the energy density and the number of pulses. This fact will make it possible to create neuromorphic computing and storage devices based on these materials. Of course, this work was carried out in collaboration in authorship. First, I would like to thank the members of my laboratory, nanophotonic and nanoosmonics, Kiselev, Burtsev, Nevzorov, Mikhalevsky, Liseyev, Ionin, the laboratory of nanostructures and optical coating, Dr. Novodvorsky, Glebov, Professor Bычkov, and our researchers of our center, Karimov, Arkharova, Milenin, and this work was supported by Ministry of Science and Higher Education of Russian Federation. So my present is over. Thank you for your attention, dear colleagues.
Thank you very much. Practical ground presentations. We have a question from Professor Konov.
As far as I know, there are many different optical devices to write some information and to erase it with thin films, like DVD discs and so on. So, what is the difference there? In your case, it is faster, or what? You also. Yes, what is the advantage? Because the approach is the same. You have to change phase. That's all.
Thanks for question. Yes, first it's very faster.
So speed is important.
Speed, yes. We talk about a few hundred picosecond, and in DVD, CD used nanosecond.
They don't need such.
Nanosecond, and doesn't use the multi-level writing.
What do you mean by multi-level?
In диск. Русском можно? В дисках используется немногоуровневая запись. Там идет точка-тире.
Ну да.
Да. А здесь мы говорим именно о многоступенчатых переходах в одной области путем глубины воздействия на PCM. Да.
Есть промежуточный. Да.
Пенка, извините, я тоже давно по-русски приготовился по-английски. Два вопроса. Первый вопрос. Ну, всем понятнее, я думаю. Первый вопрос вот какой. Не наблюдали ли вы деградации глубины по мере увеличения количества вот этих вот переходов, аморфизации, кристаллизации и дальше?
Нет, не наблюдали. В этих материалах запись-перезапись сообщается о 10-12 степени, возможно.
Нет, да, возможно. Но при этом материал себя ведет так, что он не до конца аморфизируется, потом не до конца кристаллизуется и так далее. И это имеет конец. Вот. Ну, я занимался вот буквально тем же в других материалах, ну, в керамиках фоточувствительных. И там, да, мы тоже все это видели, все это хорошо, но когда много этих самых, много раз перезаписываешь, то потом оно деградирует, перестает откликаться так же быстро и так же глубоко. Не наблюдали.
Ну вот в тех экспериментах, что мы проводили, там, это десятки перезаписей мы делали. Задача не было как бы предельно это. Вот десятков перезаписей такого мы не наблюдали. Да, эти материалы телевиду известны тем, что они окисляются. И, естественно, в части экспериментов это были открытые пленки, но для использования в устройствах это нужно защищать, безусловно.
Ну, до использования в устройствах еще 100 лет, и неизвестно.
Да, деградация возможна.
Там же много всяких других требований, это оставим.
Да, согласен. Да.
Понятно, как флажок. А второй вопрос такой. Значит, у вас механизм чисто тепловой.
Да, мы полагаем, что...
Ну, в принципе, возможен как тепловой, так и фотохимический. Вот если вы посмотрите, я с этим сталкивался. Конечно, теплом можно все нагреть, и там все активируется. Но если вы посмотрите их спектры, если там есть какой-то агент, какой-то ион, который меняет, скажем, свою валентность, есть и фотохимический механизм. И тогда это все гораздо эффективнее.
Мы с профессором Шкуриновым это очень плотно обсуждаем, как раз именно попробовать не тепловые.
Я могу ответить, что никаких ионов там нет. Давайте с этого начнем. Это чисто ковалентный полупроводник, и никакие валентности там не меняются. Значит, у меня вопрос следующий. Имеет ли смысл говорить о неких multi-level состояниях, когда у нас их там, 4, по-моему, да? Ведь чтобы было 1, 2, 3, нам нужно как минимум 9, по-моему, да, так устойчивых. А когда там 3-4 состояния,
Почему 3-4?
Ну а сколько там?
Сейчас покажу. Вот, пожалуйста, до 15 получается, нет проблем. Другое дело, что, конечно, закон Бугля не обманешь, там есть, поэтому больше, конечно, наверное, не получится. Хотя были в наносекунду я показывал 3-4, да.
Просто надо как минимум 9, да, чтобы было 1, 2, 3.
Это просто было ограничено возможностями нашими техническими с настройкой лазера наносекундного.
Thank you. I have also a question about thermal resistivity of this device. How high could be the temperature when it stops working? Because you have some melting point, probably it's not very high. What is the melting point of this material?
Melting point is about 980.
900?
900.
Ah, okay.
Kelvin.
So it's very much. Kelvin.
Kelvin.
Still much.
Yes.
Okay. And the lowest energy state corresponds to the crystalline phase. Yes.
Yeah, of course.
Okay. And you amorphize it again only due to short solidification time because it conserves disorder which is implemented by the high energy pulse. Сделать его аморфным снова, вы используете больше энергию.
Да. Демонстрация требуется больше энергии.
Okay, thank you. Some more questions, please? Okay. Let us thank again our representing NASA.
Thank you.
And at that, I would like to invite the next speaker, which will give his talk online. It's Professor Malashkevich. It is the third one, because the first one was not given. We've started from the second, and now it's the time for the third. Professor Malashkevich. Excitation of rare earth ions luminescence in glasses by satellites of Raman scattering. Professor Malashkevich is from Minsk, from Belarus. National Academy of Science, Institute of Physics. Hello. Yeah. Do you hear us? Do you hear? We do not hear you. Try to say something, please. Какой микрофон он слышит? Этот слышит? Да? Ага. Okay, hello. You can start. А презентацию он ставит или вы? Yeah. That's your time, Professor Malashkevich. That's your time to make a presentation.
Now.
We can hear you. Please let us see your presentation.
Just a moment, please.
Okay.
Yeah.
That's it.
Dear colleagues, this work was done in cooperation between this institution. Objectives: elucidation of causes of rare earth ions luminescence excitation in solid state matrices beyond the absorption bands of these ions. About 10 years ago, a rather effective laser excitation of ytterbium-3+ ions in some glasses beyond their absorption band was reported. This effect was explained by the formation in the glass of a continuum of defect centers with excited states in the matrix transparency region, and the transfer of excitation from them to the rare earth activator. This interpretation seems unlikely, at least because of the absence of luminescence of the high purity matrix when excited in the region of its transparency and lowering the temperature down to 20 Kelvin. More likely, excitation through the hard to remove impurity of widespread prevalent ions are weakly absorbed in the entire visible region of the spectrum. The lower metastable state of ferrum-3+ ions at coordination number equal to 6 is characterized by wave number of about 10,000 and 550 inverse centimeter, which is about 300 inverse centimeter higher than the lowest arc level of the metastable state of ytterbium-3+ ions, and is the reason for the effective excitation transfer from the former to the latter by the exchange resonance mechanism. Moreover, it was found that ferrum-3+ can sensitize the luminescence of some lanthanide ions by the excitation transfer from the intermediate levels above the ferrum-3+ metastable state. Therefore, purification of reagents from impurity iron is of primary importance in determining the correct cause of the effect in question. Materials and experimental procedure. The glasses of this system with composition near stoichiometry of Huntite obtained from special purity grade reagent and activated by ytterbium-3+ and terbium-3+ ions were used for research. The impurity iron in the investigated samples, judging by the results of the electron paramagnetic resonance study, a G factor of about 2.0 and 4.3 was absent, at least in the concentration of more than 10 to the 15 power ions in cubic centimeter. Absorption spectra were recorded on the spectrophotometer. Luminescence and Raman spectra were recorded on a spectrograph where the CD camera Hamamatsu was used for recording of emission spectra. The samples were excited by radiation of the second harmonic of neodymium laser and a tunable laser of Sophia with titanium pulse. Titanium pulse half-width of about 10 nanoseconds. The detected signal decay kinetics was investigated by means of the digital oscilloscope and the monochromator and the photomultiplier. Results and discussion. As a result, it was found that the emission spectrum of non-activated glass a series of low intensity weakly resolved bands which disappears simultaneously with the excitation pulse is observed on the long wavelength side of the excitation band. The excitation band equal lambda excitation band equal to 532 nanometer. This fact allows us to connect this band with Raman light scattering. Judging by the literature data, only this band can be associated with vibration of chemical bonding of boron with non-bridging oxygen atoms, while the remaining bands are due to vibration of structurally bonded water. This curve is infrared absorption of the glass, and the band is absorption of hydroxyl ions. Next slide shows absorption spectra, luminescence spectra, absorption spectra, luminescence spectra reduced to the same quantum intensity of the excitation pulses as well as Raman scattering spectrum of glass with this composition. The rows correspond to the excitation wavelengths and wave number of the Stokes satellites. Their color coincides with the color of the corresponding luminescence spectrum. Interesting that terbium-3 plus ions luminescence intensity correlate with the intensity of the Stokes satellites of Raman scattering. This figure shows that the luminescence intensity of terbium-3 plus ions is almost linearly dependent on the excitation intensity. This figure shows that for terbium-containing glasses, a good correlation of their luminescent terbium intensity takes place for these satellites. But is broken for the high frequency ones. This fact may testify in favor of the different degree of interaction of rare earth ions with high frequency impurity oscillated, in our case, hydroxyl ions. In this line, we suggest a simplified scheme of excitation of rare earth ions, luminescent by Raman satellites. We have shown this process since sensitized lanthanide 3 plus ions luminescence is also observed at excitation with a smaller Raman shift in comparison with considered above. The above results allow us to conclude that observed excitation of luminescence of rare earth ions in solid matrices is the result of the radiation-free transfer to these ions of excitation from stock satellites of Raman scattering of incident light. This effect can be used to study the interaction of these ions with the host matrix and the impurity vibrational oscillators included in it, and to obtain the metastable state population of activator uniform over the volume of matter. Thank you for your attention.
Thank you. Are there any questions? I have a question. So on the diagram you showed us, the upper level is a virtual one, right? The level of the primary level to which photons is coming, the electron is coming, is virtual. Yeah, it's a virtual energy state. So in this case, there should be some polarization dependence between probably the emitted light and the light corresponding to the excitation. Did you observe any?
We have not polarization research. This investigation we will in future.
So you didn't look for polarization. Another question, there should be some non-linearity in this process. Is the process linear with respect to intensity of exciting radiation? It's linear.
Linear.
Okay, thank you. Why wouldn't you consider the possibility when these electrons high above are going down through the intermediate levels, not by using this virtual state energy? Non-radiative transition.
This transition, this transfer is non-radiative transfer.
Yes. I mean, why wouldn't it possible if you would fill the space from the upper level to the level 2, for example, by the set of small steps of levels which would provide non-radiative transition?
I don't understand your question.
Okay, okay. Thank you again. No questions? No more questions? Thank you.
Thank you, dear colleagues.
Due to changes in our schedule today, the next presentation will be given by Professor Samokin. Alexander Alexandrovich, we give you the floor, please. Alexander Samokin is from Academy of Science, from the General Physics Institute, and his talk is entitled Pressure Pulses in a Nanosecond Laser Ablation of Mercury due to metal nonlinear transition. Non-metal, yeah, I do not see it clearly, sorry. Metal, non-metal, analysis of the results, of the experimental results. That's made together with Pivovarov, who is an experimentator. Okay. Да.
Good afternoon to everybody, and I dare say it in Russian. Добрый день. Извините за недопустимый язык. I try to deliver my presentation in bilingual, Russian and English. First, let us begin with some important preliminary notes. Experimental and theoretical investigation of laser ablation in near-critical region of liquid-vapor phase transition in irradiated matter remains one of the long-standing unresolved problems in laser-matter interaction. The problem concerns in particular with metal-non-metal transition and explosive boiling in superheated liquid metal. Due to this fact, critical parameters for most metals are known very badly, as it was already mentioned many times before by many authors. Some remarks of the kind one can see on the following 3 slides. From the paper of Komkin and Shumichin. However, the parameters of critical points were determined only for alkali metals and mercury, while the study of other metals encountered significant difficulties. As a result, data on the critical parameters and binodals for most metals are still missing. That's enough. For example, aluminum, critical pressure. You see the dispersion of the result, estimation results, and about of order of magnitude. Order of magnitude in pressure. Theoretical estimation, experimental results are absent. Further example. This is a report of Yasilevsky and Gryznov at Snezhinsk, very famous place. Very old and not resolved yet problem of extreme uncertainty in our knowledge in location and critical point parameters for uranium and its compound is under discussion. The expected critical region for uranium is not presently achievable experimentally. At the same time, traditional way of theoretical estimation for critical parameters on the basis of far extrapolation of well-known low temperature thermal and caloric properties for condensed phase lead to extreme dispersion in predicted values for uranium critical temperature and pressure. In Russian it sounds like that. Скандально большой разброс. In the Russian version, others. And they mention about possibility for existence of hypothetical additional entropic phase transition similar to that predicted by Landau and Zeldovich long ago. The next slide demonstrates some papers on the problem. This is a paper of Landau and Zeldovich on the relation between the liquid and gaseous states of metals. 1943. It's really long ago. And one of the latest paper, nanosecond laser, on the metal-non-metal transition under nanosecond laser ablation. Two main experimental results from this paper. Formation of additional pressure peaks on the pressure pulse. Reduction of the observed propagation time of the pressure signal from the radiated region to the piezoelectric sensor. The pressure behavior, this is shown together with the reflected laser pulse evolution as growing radiation intensity in the following two slides. This is the previous experimental results. Here, laser pulse and reflected pulse. Reflected is some lower. And this is a pressure pulse. This is thermoelastic or thermoacoustical pressure. And here you can see additional pressure due to vaporization effect. This is mercury. And this fact can be used for pressure sensor calibration to simultaneous signal, thermoacoustical and pressure signal. And the following evolution is evident. Pressure signal grows much faster than thermoacoustical. And then new peak appears on the pressure signal, while the reflection signal changes but little at the low intensity where vaporization is already present. And evolution, the new peaks as follows. This is the new peaks. It grows faster than vaporization peak. And simultaneously you can see that the arrival time of the pressure signal is diminishes as compared with low intensity case. You see the difference about 50 nanoseconds. It should be mentioned that the whole time is about microsecond. So it is not very much as compared with the whole arrival time, but very important delay. And in this presentation, we discuss some theoretical estimation of this behavior in the framework of two-wave structure, including metal-non-metal transition case. This is a half space of irradiated matter, laser light from the left. This is the rarefied bleached zone, просветленная zone in Russian, non-metal rarefied state. This is compressed metal state, compressed due to shock waves. This is boundary shock wave and this unperturbed matter, and this is boundary between non-metal and metal case. If we use in quasi-static process usual boundary condition on these two fronts, we can obtain some useful for further discussion relations. This is the velocity vaporization front, about 14 meters per second. correspondent pressure, which is about half of saturated pressure, is about half of the 1,000 bar. At corresponding temperature, about 1,500 kelvins. And if we use this relation and corresponding numerical values, which is for mercury critical value here, here, and here, and at the metal-non-metal transition there something low, we can obtain such dependence of the recoil pressure with absorption density in a quasi-stationary regime. This is the vaporization regime, and this growing part is due to movement of metal-non-metal transition front. And because we can make the following step. We have two experimental values, pressure and change in arrival time. So we can compare these parameters with known shock wave data for mercury. And we obtained not very good, but sufficient results for in comparison of these two cases. Important notes should be said about calibration procedure. As I mentioned above, calibration pressure at low intensity, which use comparison thermoacoustic and vaporization signal, in this case should be changed to comparison with vaporization and thermoelastic effect or thermoacoustic signal due to metal-non-metal transition. And this two calibration procedure differs by about factor about 8. There are some reasons for it, for this, but let it be later after discussion. So we have the following conclusion. From our analysis, it follows that observed in previous experimental paper recoil pressure evolution can be explained with the help of metal-on-metal transition effect in liquid mercury. This effect is responsible for additional pressure peak appearance and pressure propagation time diminution. The analysis results are consistent with independent shock wave data for mercury. More accurate quantitative data on this effect can be obtained using pulse laser action with a constant intensity distribution over the radiation spot, top hat, and piezoelectric sensors with wide dynamic range. Such experimental data can be more adequately analyzed within the framework of non-stationary numerical calculation. Such studies are necessary to elucidate all the main features of the non-equilibrium behavior of metals in the region of their critical parameters, which continue to be insufficiently studied even for mercury. Thank you for attention.
Thank you. The talk is open for discussion. Professor Konov.
First of all, I'm really surprised how well you can speak English.
And I am too.
To your opinion, what parameters are most crucial to be determined to make this model, to make this approach reaching finish or coming to the end? Which parameters are most crucial?
In experimental?
Experimental.
Experimental?
There are many parameters. If you wish to understand all 20, then it's difficult.
Not more crucial, but more achievable. It seems to me it is pressure. It is pressure. Because the temperature is hardly the measure for metals other than mercury.
Why?
Because plasma effect. In mercury, no plasma effect, because low temperature critical and high ionization potential.
So, in case of mercury, only pressure is important.
Pressure. And of course, in the case of mercury and temperature, about 1,500 kelvins can be measured, I think, experimentally, in pulse regime.
I think it could be. At the present time, I think it can be well measured.
But it is really not done for these regimes. Maybe somewhere it is done some measurement, but I do not know experiments on laser ablation regime with such measurement.
Some more questions, please. I have one. What was the energy density at the surface?
This about tenths of megawatts. That's very low. This pulse is about 30 nanoseconds, and the surface temperature is about
Energy of the laser pulse, and what was the focusing, or no focusing at all?
fluids, energy density, fluids.
Okay, fluids.
It's about parts of the joule per centimeter square.
Part of the joule, yeah. So definitely no plasma. Okay, no light. What was coming from the spot?
What?
Light, no light. You didn't see any.
Thermal.
Did you see any light from the?
Electric light?
No. I mean.
Is it shining?
Shining. Is it shining? Something visible? Nothing. Yeah. Could we possibly have a look at the plot which you demonstrated us first? Вот графики. Давайте посмотрим экспериментальные. Вот самое начало. Да, вот это. How can you explain the negative part of the pressure signal?
For thermoacoustical, this is nature, but for higher intensity, it is artifact. It's not.
Yeah, because it's a liquid, we do not expect any negative pressure in this media.
In liquid, we can gain negative pressure due to thermoacoustical signal, usually. And it is more important for more short pulses.
Yeah, but it's 10 bars.
Where negative pulse is almost equal to positive pulse.
And
Thermoacoustical.
it's not the feature which is coming from the detector of the signal.
Yes, of course it is. As I put it in conclusion, the problem of acoustical measurement is very important. As for calibration, procedure, and top head distribution intensity, and so on, so on.
And the last, what is this detail which proves that you have metal, non-metal transition on this diagram?
This fact. Additional pulse formation. This is
And so at this point, yeah, at this point it comes to non-metal. В этой точке он переходит в неметаллическую фазу.
Мы видим дополнительный, we see additional pressure pulse, and we explain it as due to metal-non-metal transition, because it can be explained due to growing of light penetration depth.
Okay, and what do you expect is the difference between enthalpy of metal and non-metal phase? What is a lower?
I can't say it for certain what is the kind of phase transition. It is first order phase transition, but details.
If it is lower for non-metal phase, you can expect some additional portion of heat.
You may consider it as recombination. Metal, it is solid state with electron plasma. Yes? But if we expand it, we obtain recombination. Not transition.
But it is much more fast.
Just opposite to metallic hydrogen.
It's,
if we press it, we from dielectric phase, instead of dielectric phase, obtain metal hydrogen. And this is the opposite, reverse effect. And as for plasma picture, it is recombination of electron plasma.
It's known to be
expansion.
It's known to be very short in metals, so definitely not in the nanosecond pulse width range. It would be shorter.
Yes, of course. Yes, of course.
Okay, okay. Thank you very much. One more question.
Do you think it is possible that you have some surface phenomena also, some formation of surface electromagnetic waves, this interference, and it can result in jump of pressure and so on?
As for you see, the vaporization peak appears, but the spectral reflection.
But you see, excuse me.
Almost the same.
You say you speak that for mercury, then you don't have vaporization. You told me that in case of mercury you have a low melting temperature and low temperature of the surface.
Mercury, here vaporization, here vaporization.
So you always have vaporization. You have vapor.
At about half thousand kelvins pressure. Here it is low.
So in this case you will have surface waves and surface structures, and reflectivity will change.
If this structure can develop for this time.
It can. This is no doubt.
No.
Such structures can be developed during peak femtosecond.
Low intensity. Intensity, you see.
They develop by femtosecond pulses.
At very high intensity. Low intensity. There are strike experiments on the evolution of capital waves on the liquid mercury. It permits such behavior. You can see mirror reflection, stable reflection, almost the same as at very low intensity, while vaporization effect is clearly visible. This is the reflection. You see, one signal, incident light, and other.
This is a reflection. What about absorption?
I say
It is
remains flat. At the
if it remains flat. If.
No. If you have a mirror, so the
Yes. But if you have surface structures, then it is no longer a mirror.
yes, of course. But we can, due to surface structure, cannot make a reflection more than 100%.
No more than 100.
The surface is flat. But this picture experiment just confirms it. We have vaporization signal, which is twice as large compared with thermoacoustical pressure. But reflection signal is almost the same as at very low pressure.
Okay, but nevertheless, reflection falls down later. Отраженный сигнал сильно уменьшается потом, когда вы...
Yes.
Yeah.
Yes. Later, what?
Okay.
Потом уменьшается. And this diminution, это уменьшение может быть разным эффектом, безусловно. И голубизной, и материальными параметрами. Так что тут это мы не привязываем. То есть это не противоречит просветлению.
Там правая подушка, она становится рассеивающей.
Там много эффектов.
Ну, пар на поверхности.
Много механизмов могут
Пленка пара.
уменьшение отражения. Вот поэтому и давление наиболее такая надежная величина для измерения. И она прямо может давать критическое. Это так связывает экспериментальные величины. Вообще говоря, неравновесные. С равновесными это серьезная проблема. Фундаментальная проблема. Это как, я уж еще у Мандельштама написано, если вы имеете время меньше периода, то вы за это время период не измерите.
No more questions. Thank you very much, Professor Samokhin. It was very interesting, and for the discussion, for the following discussion. Unfortunately, our section today is over. I would just like to remind you about the poster session at about 4, immediately after which we are going to join our recreation part of the event. The bus will be we will be given to the boat by the bus at about 6:30. Yeah. You don't forget the poster session, please. Thank you.